Okay, let's talk about colligative properties. So colligative properties are just properties of a substance that change when a solute is dissolved in that substance. So it doesn't actually matter what the solute is, um, but what matters is the number of solute particles. Okay, so how much of that solute you put in and what happens to the solute when it dissolves. Um, so it doesn't matter if you're dissolving, sodium chloride or potassium chloride. They're going to have the same effect, but that effect depends on how many particles are dissolved. Um, and so the colligative properties that we're going to look at are osmotic pressure, vapor pressure, boiling point, and freezing point. Or melting point, if you want to call it melting point instead of freezing point. So first, let's talk about osmosis, because this is what relates to osmotic pressure. So osmosis is a process in which solvent particles diffuse through some barrier that aren't going to allow the passage of the solute particles. Okay, so like in this picture at the top, we've got that vessel, that kind of flask looking thing, but at the bottom, it's got this membrane called a semi-permeable membrane. And if we place that then in a beaker of water, what you would see happen is that solution in that kind of flask, that solution level would start rising, okay? And it would rise to a certain point until osmotic pressure is reached. And so that is the water traveling through that semi-permeable membrane into that salt solution, okay? And so the semi-permeable membrane is just some kind of filter almost. It's something that allows the solvent particles to go through, but the solute's going to be trapped on the one side. So this is what happens really in our bodies, okay? So our cells are in our blood, okay? Blood is a solution, and cells are in that, and within the cell there's some solution inside of the cell, and the cell wall is a semi-permeable membrane, and so it allows some things to pass through it and other things it does not allow to pass through it. And so water can flow in and out of that cell in order to actually equal out the concentrations. And so the solvent is actually going to naturally pass from the concentration or the side of low concentration to the side of high. And so if the solvent leaves the low concentration side and goes into the high concentration side, what's going to happen is at the same time it's going to be increasing that low concentration, because if you take solvent away from it, the concentration now is going to go up. And if the solvent is going into another one, it's going to dilute that concentration, so it's going to decrease that. And so it's changing the concentration of both of those things. And this process will occur until the concentrations are equal, okay? But the process can be stopped, okay? But the reason that this happens is just because of what we call entropy. And so it has to do with everything wanting to be as disordered as possible. Okay, and so when solvent mixes in with a concentrated solution, it gives the solute particles kind of more freedom to move around in. Okay, and so it gives more randomness to that solution. And so that's why naturally the solvent goes towards the more concentrated solution, because it helps to increase the entropy of the system, which is energetically favorable. But like I said, this process actually can be stopped, and it will seemingly stop on its own But the reason that it stops when it does is either because the concentrations are equal or because something is applying a pressure to that. Okay, and so that's what's happening here when this solution stops rising in that third part of that picture. It's because the pressure from the outside, so just the air on top of it, just the gravity is pushing down on it, and it's applying enough pressure to stop that flow. And that pressure is called osmotic pressure. Okay, so the pressure required to stop osmosis or to stop osmotic flow is the osmotic pressure. Okay, so there's just another diagram showing kind of an osmosis process, but this has got a U-tube, and in the center there's a semi-permeable membrane. And so one side's got pure solvent, one side's got a solution, and so that pure solvent is going to travel into the solution until it can't anymore. In that case, if it's pure solvent on one side, you can never equilibrate those concentrations because you're never going to get solute on one side. But eventually gravity is going to stop it, or you can actually press on the solution and get it to stop. Okay, and however much pressure you need to put on it to stop it, that is the osmotic pressure of that solution. And so even if you kept pressing, if you pressed harder, then what's going to happen is actually you'd reverse the process. So you would force solvent back out of that. So you can even not only stop the process, you can reverse it by applying some pressure greater than the osmotic pressure. And that actually would be called reverse osmosis. Okay, so when the solvent is flowing from the high concentration now to the low, meaning the high concentration is going to increase even further and the low is going to go even lower, that's reverse osmosis. And that's something that does not happen on its own. It's something that you force, okay? But it can be forced. So the osmotic pressure of a solution is going to go up as the concentration increases, okay? So the more particles in that solution, the more solvent is going to want to flow towards it. So the harder it's going to be to stop it, okay? So it's actually directly related to the concentration of the solution. So the higher the concentration of the solution, the higher its osmotic pressure, okay? Whereas pure solvent has an osmotic pressure of 0, okay? But anything with a concentration has some non-zero osmotic pressure, and it's going to be higher the higher the concentration is. Now, we're not going to look at calculating that. You can, there's an equation for it, but we're not going to go that far in. You should just understand that if you put more solute in there, you're going to get a higher osmotic pressure. Okay, now one application or one place where this comes up, osmosis comes up, is in our bodies. Like I said, it happens in our blood where water can flow in and out of the cells. And so if you were to go into a field where you were dealing with blood or anything like that in the human body or even animals, you may hear the terminology associated with osmosis in the blood. And so they'll talk about a solution being hypertonic or hypotonic or isotonic. And that has to do with if the concentration of that solution, whether it's higher than inside whatever, and so in this case, inside the cell, so the blood's concentration versus the concentration in the cell. If it's higher, it's hypertonic. If it's lower, it's hypotonic. If it is equal, it's isotonic. And so remember, if it's a higher concentration, then solvent is going to flow towards it. Meaning in this case, the place where you can get more solvent would be within the cell. So then water would flow out of the cell into the blood, which would cause the cell to start to collapse, okay? And so eventually that could be a bad thing if too much water comes out of the cell. But if you have a hypotonic situation where the blood has a low concentration, that means that the water from the blood is going to flow into the cell, which that can be even worse actually, because eventually that can just burst the cell. You can kind of recover from the cell collapsing by, diluting the blood, and eventually it'll kind of re-expand that cell. But if your blood's concentration is too low, then it could start to burst cells because too much water is flowing into the cells. Whereas if you have an isotonic situation, that's essentially your equilibrium situation where the concentrations are equal. So your body's kind of happy. It's nothing is flowing in or out, or if it is, it's going both directions. And so like if you go into the medical field and you're giving IV solutions, or you go to the hospital and you get an IV, they give you a solution most often that should be isotonic with your blood, okay, or with your cells. Now, if you're in a scenario where your cells are too far expanded or they're too far collapsed, then they might, give you a solution that has a higher concentration or a lower concentration to reverse what's going on. And so that all is tied to osmosis and osmotic pressure. Now, another colligative property that we want to look at is vapor pressure. So you need to know vapor pressure is the equilibrium pressure between the gas molecules above a liquid and the liquid, okay? So you have an equilibrium where you have liquid particles evaporating, and at the same time you have gas particles recondensing into the liquid phase. And so it is at equilibrium, so the rates of those are occurring at the same time. And that's the measure of the vapor pressure, is the pressure of that gas above it. Now, vapor pressure does increase with increasing temperature, so it is something we could manipulate by changing the temperature. So if you wanted to increase the vapor pressure of something or decrease the vapor pressure of something, you could simply heat it up or cool it down, okay? Now, it also is related to the intermolecular forces of the substance. So it in some ways is a characteristic of that substance, because the intermolecular forces are due to the structure of that substance. Now that part you can't change, or you're changing the substance, right? But if you have a particular substance and it has certain intermolecular forces, they have a given strength, then that's going to control how much stuff can escape into the gas phase, okay? So different substances have different vapor pressures, okay, at a given temperature. But any substance you can heat up and cause the vapor pressure to go up, or you can cool down and the vapor pressure will go down, okay? But if we just consider we have this substance at a set temperature, what else can change the vapor pressure? And that would be dissolving something in it, okay? So it is a colligative property, so if we dissolve something into this substance, it'll cause its vapor pressure actually to go down, okay? And basically, anytime you dissolve something into a liquid, the vapor pressure of that liquid goes down. Now, by how much depends on, how much stuff you're dissolving. So how many solute particles are going into that solution. But the reason that this happens is because your solute particles that you put in that solution, it slows the rate of evaporation of those solvent particles. So remember, vapor pressure is when It's the pressure above that solution when you have some things evaporating and some things condensing all at the same time, right? But if they're evaporating slower, now more stuff is going to get captured by the solution and the resulting pressure above it's going to be lower, okay? And the reason this happens is because when we add solute, now the entropy of that solution is higher, okay, than what it is as a pure solvent. And that's because there's more randomization in there now, because there's more different types of particles. And that's a favorable situation when you have more entropy. So that means now your solvent particles want to stay. They don't want to leave as much. And so you have a lower vapor pressure. And that is directly related to how many particles are in solution. So just like osmotic pressure is directly related to concentration, if you add more particles, your osmotic pressure goes up. Okay, and the more you add, the more it goes up. The same happens for vapor pressure, but it's going down instead. Okay, so if you add more particles to a solution, the vapor pressure goes down. Okay, so the concentration of your solute, as it increases, your vapor pressure of the solvent goes down. We're not going to look at any calculations involved with the vapor pressure. There is an equation for it. That one's actually, it can be complicated, but you just need to know that, you know, the basic relationship that vapor pressure decreases with increased solute concentration. Now, next one we want to look at is boiling point. So boiling point is the temperature at which the vapor pressure is equal to the atmospheric pressure, or in other words, it is when the liquid and gas phases are in equilibrium. So the first explanation there is the technical definition. And when those pressures are equal, it means that there's nothing really holding those liquid particles in the solution anymore. They can freely escape. That's why those phases are in equilibrium. But boiling point is another colligative property. Boiling point actually elevates or increases when solute particles are added. So the boiling point of a solution is always higher than the pure solvent. Okay, so let's say we have water under standard conditions, 1 atmosphere. It has a boiling point of 100 degrees C, right? But if we dissolve stuff in that, its boiling point now is above 100 degrees C. And how much it increases depends on how much solute you dissolve in there, okay? And for that, it's tied directly to vapor pressure, okay? Because since boiling point is tied to vapor pressure being equal to atmospheric pressure, and we just said vapor pressure goes down when you dissolve solute. Well, if I dissolve solute and the vapor pressure goes down, now I'm going to have to put in even more energy to re-increase the vapor pressure, meaning the boiling point is going to go up, okay? So the boiling point has to go up if the vapor pressure is going down. And so this one also is directly related to how many particles are in solution, okay? And so more particles in solution, the higher the boiling. This one, I'll give you the equation for it. And this equation actually shows you the relationship between the elevation of the boiling point and the concentration. Okay, so the delta TB part is the boiling point elevation. So it's not the actual boiling point, it's telling you how much it's going to increase. So if you know the delta TB, you add that to the boiling point. So if it's aqueous solution, you calculate this and you add it to 100. Okay, so it tells you how many degrees above the boiling point it's going to go. The KB is just a constant, a boiling point constant. It is specific to the solvent, okay? So if it's water, look up the KB value for water. And that is all dependent on the structure of that solvent. And so the intermolecular forces of it are going to impact that. And so you have a different KB for different solvents. And so those are values you look up in a table. And then the molality. The molality is the concentration. And so that is like any other molality. It's the moles divided by the kilograms, but it's moles of the solute. And so the solute particles, whatever they are, divided by the kilograms of the solvent. But either way, no matter what unit of concentration, it would always be true that you increase the concentration of your solute particles and your boiling point's going to go higher. Okay, the higher you increase that concentration or the more solute you put in, the higher the boiling point's going to be. Okay. Now the last one we've got is freezing point, and this one, well, freezing point, you should already know, is the temperature at which your liquid and solid states are at equilibrium. So you can also call it melting point if you want. Okay, so it's the temperature at which those transition. And so this is opposite of boiling point. Instead of elevating, which, oh, I have a typo there. That's what I get for copying and pasting things. This should say freezing point depression. Sorry about that. Freezing point depression. And so the freezing point decreases. It's always lower than the pure solvent. So for instance, if we have water and we dissolve something in it, well, water has a freezing point of 0. So if we dissolve something in water, the freezing point is going to be something below 0. Okay, that's why in the winter they put salt on the roads, or even a salt solution sometimes, some places. And that's because they're essentially putting down solute. And so when the snow falls, okay, and it starts to melt, it actually will start to melt even below 0 degrees C because of those solute particles that then start mixing with it. Okay, so it decreases the freezing point so it can be even colder outside and not frozen yet. Now, the reason it depresses, you can actually tie that to the boiling point and the vapor pressure, but that's a little more confusing of an explanation. And so I think the best way to think about it is essentially you're throwing these solute particles in, and in order for something to freeze or go into the solid state, all of these particles need to line up just so. Okay, so in the solid phase, things line up in this very nice ordered arrangement. But if there's solute particles now there, then it kind of disrupts that nice arrangement. And so you actually end up having to take more energy out to get it to settle down into a solid phase. Okay. And so this actually you can calculate just like you can boiling point elevation. You can calculate the freezing point depression. And that is a similar relationship. And so the higher the concentration, the more it changes. Okay. But in this case, it goes down. Okay. But this equation, again, it is not directly calculating the freezing point. It is calculating how much it changes. And so, and again, yeah, I have copy paste error here. It's a depression. It's not an elevation. Okay, so when you calculate the change in freezing point, you would then take the original freezing point and subtract this value, and it would tell you the new one. This also is just some constant times the molality of the solution, and that constant, it's the Kf, not the Kb, so there's a different constant, there's a different impact that dissolving something has on a boiling point than it does the freezing point. Okay, it's not going to be the same number, but it is specific to whatever your solvent is. Okay, so water has a specific Kf, whereas other solvents are going to have their own Kf, and you just multiply it by the molality. And so the higher the molality is, the greater your change in freezing point is, meaning the more it's going to go down. Okay, now with all of this stuff, what you need to realize is that it depends on the number of solute particles, okay? So be very, very, very careful. Remember, we can have different types of solutes, okay? So you can have strong electrolytes, you can have weak electrolytes, you can have non-electrolytes. And when you dissolve them into this solvent, different things happen. So strong electrolytes break up completely, right? They break up into ions, meaning we put in a certain number of things and now we have more, okay? So if it breaks into two things, now we have twice as much as what we put in, okay? And so you've got to be aware of that. Whereas if you have a weak electrolyte or non-electrolyte, pretty much what you put in is what you get. Now, a weak electrolyte does dissociate a little bit, but it's pretty close to the original amount that you put in. And for a non-electrolyte, it is the same amount. But for a strong electrolyte, it dissociates, so you have more stuff, okay? So usually when we talk about a solution's concentration, we talk about it in terms of the intact thing, whereas solute particle concentration could be higher, okay? For a strong electrolyte, it is definitely higher, okay? So for instance, sodium chloride is a strong electrolyte. So if I have a 1 molar sodium chloride solution, in reality, I have a 2.0 molar solution of particles, okay? And that's because sodium chloride, when we dissolve it in water, we get Na plus and Cl minus. So for every 1 NaCl, we get 2 particles. So the concentration is double, okay? And that makes a huge impact on the colligative properties, okay? So there's twice the change in the colligative property as if you would have put instead a non-electrolyte, okay? So they have a greater effect on colligative properties, your strong electrolytes versus your weak and your non. Now, weak electrolytes will have a greater effect than a non-electrolyte, but it's not going to be a huge difference, okay? So the big thing is that your strong electrolytes have a bigger difference, meaning you're going to have an even higher osmotic pressure and an even lower vapor pressure and an even higher boiling point and an even lower freezing point than a weak electrolyte or a non-electrolyte, okay? So for instance, if we wanted to compare the strong electrolyte sodium chloride to the non-electrolyte glucose, well, if you had a 1 molar solution of each, well, the sodium chloride really breaks up into 2 particles, so you really have a 2 molar solution versus a 1 molar, meaning the sodium chloride is going to have a higher osmotic pressure and a higher boiling point than an equal concentration of glucose. And that's because the sodium chloride splits into more particles, okay? Whereas the vapor pressure and freezing point of this equal concentration of sodium chloride and glucose will be lower for the sodium chloride solution because the sodium chloride solution actually has more particles, okay, because they split up. So that's really important to realize. So that's why, like when they salt the roads in the winter, that's why they use salt, not sugar, okay? If we put sugar on the roads, you get a 1-to-1. For every particle you put out there, you get 1 particle. That's that. But if we put salt out there, depending on which salt you pick, you get more particles. If you use sodium chloride, you get a 2-to-1. So for every 1 mole of sodium chloride, you get 2 moles of particles. But if you use something else, like you could use, sodium phosphate, you'd get 4 particles because you'd get 3 sodium ions and 1 phosphate ion. And so salt can actually have a bigger impact on colligative properties than like sugar, because that's a molecular compound. Okay, so that's the basics of colligative properties. As I said, we're not going through bunch of calculations, you should understand the basic relationships. So the general idea of this increases or decreases when we add solute, and the more solute you add, the bigger the impact it is.